So what are you guys?
We're the SWARTWOOD family.
And remember, the two big assumptions you're making throughout are, even though they sound simple, is the fluid is incompressible. I know that sounds stupid, but we'll actually use it. And the second thing is there's no viscosity, no gooiness. Okay, so continuity equation. We'll just do it with an example. So here I've got this guy. I guess I could draw a little bit better than that. Sorry. Okay, and it's filled with fluid. And the fluid's moving. Okay, so a couple ways to do it. Intuitively or the mathy way, doesn't matter. So what I do is I take a little section here. Okay, and it turns out that crossing that line in a given second is that amount of fluid. And let's pretend that amount of fluid is 1 liter. Because the fluid's incompressible, it has nowhere to go. So this thing's full of fluid and I move 1 liter over here, you can't squeeze this down. So what has to happen at this end? You have to move what? 1 liter. Otherwise there's no space for this water to go into. Everybody agree? So if you move 1 liter over here, because there's nowhere for it to go, the water has to move over 1 liter. Okay? And then if we just draw it over here, it might look something like this. That makes sense. There's a little like sliver of water, okay? And it's moving past some line here, but let's say it takes also 1 second, right? So if I move a liter over here in 1 second, because you can't compress the fluid, the water over here has to move the same way, right? So in 1 second, 1 liter has to cross this line, okay? Give me a qualitative observation here. Because this guy is skinnier, in order for you to move 1 liter, you kind of have to haul butt from left to right. Because this guy is thicker or wider, right? In 1 second to move 1 liter, you don't have to go as far, you don't have to move as much from left to right, because you have more of this. Does everybody see that? Because it's wider. Okay? Because it's wider, I have to do less from left to right. So what does that mean? That means as the cross-sectional area goes up, to get the same volume, you don't have to move as much from left to right. But if you move less from left to right in a given amount of time, what do you call that? Change in displacement over time. Velocity. The velocity goes down. Does everybody believe that? Do you want to see it the mathy way, or is this qualitative way good enough? Is it good? Huh?
Sorry, can you explain that?
Sure. So what's happening here is this is small, that's big. So as the cross-sectional area gets bigger, in order for you to cover a liter here, you have to haul butt from left to right. But because this is wider and you get a greater amount of fluid this way, vertically, right? So to move 1 liter from left to right, you don't have to move as much in a given amount of time. So the velocity here is less. So to get 1 liter over here in the picture, you haul butt from left to right. To get 1 liter over here in the picture, you don't have to move as much from left to right. So as the cross-sectional area goes up, the velocity goes down. Okay? Then that gives us two possibilities. It gives us this, or it gives us this. Oops, that makes no sense. But you know how to think of this stuff. If you see that equal to sign, you can assume here this is a constant, just so we can get a handle on it. Let's call it some other constant, like k. Okay. Then what's going to happen? What do you think? Do you think it's top equation or the bottom equation? Bottom. And you know that because we just argued, if the cross-sectional area goes up, the velocity's got to do what? Goes down. But if you're multiplying to get the same number, if one number goes up, the other has to do what? Go down. Okay? Now we didn't formally show this, so if you want to, we can go back and do the math. It's the same sort of logic. So go back and do the math or let it go?
Let it go.
Let it go? Okay. So I get it. So the equation that we get out of this must be A1V1 equals A2V2. But the intuition we get is one goes up, the other goes down. That's it. That is the continuity equation. Okay?
That's cool.
How could they test this? If they wanted to, they can test it just like this. If I decrease the cross-sectional area by a factor of 2, what happens to the velocity of the fluid? So again, think of this like a constant, right? So if I decrease the cross-sectional area by a factor of 2, that's equivalent to multiplying by half or dividing by 2. What do I need to do to keep it the same? Increase the velocity by 2. Okay. What's pretty much the same question, but in a slightly more annoying format? If I decrease the diameter by a factor of 2, what happens to the velocity? What do you guys think? If I decrease the diameter of the tube, so decrease the diameter by a factor of 2, so multiplying it by half, right? What's going to happen to the velocity? It's not the same. It's got to be a factor of 4, right? And because we're talking about area, and you know in these tubes, right, if we have a guy like this, the area is pi r squared, right? So what happens though? So if I make the diameter go down by a factor of what, 2, so it's half as big, but the radius is half the diameter, so the radius is also what? Half as big. But if you get that factor changing, so the radius is now half as big, but you're squaring, so you're making the area 4 times smaller, right? So you're multiplying by 1/4. So to compensate for that, the velocity needs to be what? 4 times bigger. Okay. So is everybody okay with this? Can we send this away? That's it. Nice topic, done. Now, we'll assume this tank is super huge. So if the tank is super huge, water is going to gush out this end, but that's a tiny opening. So this is not going to drop very much. It's going to drop so little, you can take this velocity to be 0. Okay. And let's take a height here. Height for the tank is 100 meters. Height for the spout is 10 meters. Okay. Obviously, you know, if I ask you, what's the velocity of this guy coming out of the tank? How do you do this? You think this is Bernoulli's or the old stuff? Sorry. Bernoulli's, because the fluid is moving. You know, it's not going to be that bad. We start to write out Bernoulli's, so whatever this is. Okay, so let's practice this. Number 1, maybe we'll take this as our starting point. What's the velocity there?
0.
Now, I remember when we did the pressure stuff, and we did this guy? We measured that height from the surface on down, right? But remember how we derived this? That's the only reason I did the derivation, just the concept thing. We did this from energy. And it's energy perspective usually from the top down or usually from the bottom up? Bottom up. So I guess that H1 we can take what?
0.
Maybe 100?
Yeah.
Everybody see that?
Wait, top down, bottom up.
So remember this H, if it were 10, it would really be top down. But you saw when we derived that, we did that in potential energy, which is usually measured how? From the bottom up. So I'm going to take this to be 0. You don't have to, but I will. And I'll make this obviously 100, right? Okay, so we're going to get P1 plus rho G 100 is equal to P2 plus, what height are we going to? 10, you're right. So I know what you're saying, but let's say 10 for the moment. And this thing about top down, you don't really lose that concept because 100 and 10, the difference is 90. You're totally right. 100 apples minus 10 apples is 90 apples. So you'll see that again. Okay. Oops. Okay. So we're almost done. Help me finish this. What is the external pressure on this body of water pushing it down? 1 atm, atmospheric. But well, how do I imagine the other pressure? Going with this guy or against this guy? Against. This guy's forcing the fluid that way, so we have pressure this way going against him. What do you know about this pressure and that pressure for the most part? Same. So now we get this. It looks even better because the rows go away. So now we have 100 apples versus 10 apples. Subtract, you'll get 90. And that's 1/2 V2 squared, right? Whatever that is. So it looks something like that. Is everybody okay with this? Good, good. I mean, there I just made G10 and then did some stupid math.
The only reason why you crossed out the rows is because the pressures were the same? Or
Oh, no. The rows, you mean these rows?
yeah,
Oh, because it's just there.
Okay.
I could do it.
You can do that.
Yeah. I couldn't do it in the beginning because these guys didn't have a row. Do you see that? So if I try to divide by row and divide by row, this would be P2 over row and P1 over row.
Oh, yeah.
But since I was able to get rid of the P's, then it's easy to divide by row.
Okay.
Okay? Everybody okay with this?
Could we choose like where 10 meters is 0?
Absolutely.
That's what you're
Yeah. You could have made this 0,
Just cancel.
and then the height would have gone 90, right?
Right.
And then the right side, the height would have been just 0. Totally fine.
And
But-
why are the pressures the same?
Because they're both atmospheric. Okay. Real life, this will probably be slightly different. But for the tests and also how we're able to do this problem, you say they're basically the same. Okay. So let's talk a little bit about lenses. Now that we have the whole mirror thing down, it's going to be a piece of cake. So again, the best words I think are converging and diverging. So I'm going to start with a converging lens. And the way I think of a converging lens is it reminds me of football. So if you want to convert down, so like in football, converging lens, it looks about the same. Okay. But anyway, the idea is this. We put light coming from somewhere, right? Could be left or right. In all the pictures I'll draw, just to be simple, we'll put it on the left, but it doesn't matter. You can put it right or left, okay? All right, so we have our object. Light will come from this object, hit that lens, and the rays will bend together, okay? The whole point of converging. Okay, I get it. So like usual, the conventions here, the object distance must be positive because you have a real object Light is coming from this guy. Okay? All right, the second thing, do you remember a mnemonic? Converging is always a good thing, right? Bringing friends and family together, always good. So that focal length is always positive. No big deal. Now the only thing that's kind of different, and that's going to be the image. What happens to that image? So we'll do it first as a mnemonic. What's a lens's job? To let light go through or bounce back? Well, it's clearly let it go through, right? It's a mirror's job to have you bounce back, but it's a lens's job to have you go through, right? So anything going through is doing what it should do. So an image on the right here with light coming from the left would be positive. Okay? Light rays go and they physically pass through that lens. So if you saw some sort of image over here, you know things would be right because that's where the light rays are physically meeting. Does everybody see that? You have real light rays converging to form that image. Okay, no big deal. Obviously, if we go to the other side, right? A lens's job is to let light go through, not to have it bounce back. So if for some bizarre reason you had an image over here, it would definitely be negative or virtual. And of course over here, the object's going to be negative. No big deal. And I think we're good. So that is it. Not too bad, right? I do want to point out one more thing though, and that is kind of this. With the lens, it's a little bit different because you can come at it either way. With a mirror, there's only one side you can bring real light from. But on this guy, you can bring light from the left or from the right. So really, if this is truly a converging lens, it shouldn't matter what orientation we have, it should still seem converging. Okay, so from the left to the right, it definitely looks converging because these light rays come in and they're bent together. Does everybody see that? But what if I were to run this from right to left? Even if I ran it from right to left, the action should still look converging. So if we run it from right to left, these guys would pan out like this. Here, at least in this picture, they don't converge, they just go out like this. Does everybody see that? So now the question is, why is this guy still converging? Well, think about what would have happened. If you didn't have this lens, these suckers would come out like this. Does everybody agree? But because of this lens, they're going to bend together. Okay? So that is it. So what matters is not whether the light rays actually converge. What matters is what the action is, right? Is it a converging action or a diverging action? Okay, piece of cake. Oh, by the way, my bad. One last term. I like this setup. It'll never be confusing. Converging is always a good thing. The focal length is positive. But do you remember the whole concave convex thing? If you're viewing it from this side, this thing is pushing out towards you, so it's not concave, it's convex. And if you're facing this way, same thing. This side's coming toward you, so it's convex. Sometimes old school, if you look at both surfaces and describe them, they're both convex, right? So you call this biconvex. So either biconvex or convex, when they say that, they really mean a converging lens, okay? It's kind of a pain in the butt, right? Because when mirrors, convex meant what? Diverging. My advice to you would be this. Really try to think in terms of converging and diverging, not so much concave and convex, but know what those guys refer to, okay?